Going over the quiz questions. Number 1, the P waves and the S waves are what types of waves? They are seismic. Seismic waves. They're waves that travel through the earth. What's the difference in an S wave and a P wave? S waves are which type? Oops, got to take that off.
S waves are the shear.
Okay, shear. That's great. S waves are shear waves, which means that they are transverse. Well, a shear wave is going to be transverse by the definition of what shear means. Thank you. So S waves are shear waves or transverse waves. The P waves are, what kind are they? Pressure. And pressure is an example of longitudinal. So pressure doesn't mean longitudinal like shear does, but that's what the P stands for, primary or pressure. This S, secondary or shear. Okay, how many major tectonic plates? 8. Everybody got that? Or everyone I looked at, I should say. I don't want anyone to feel sad if they didn't. What type of rock is produced, is the product of heat and pressure applied to, and the student who put this in put igneous rock. You could have put any rock there. Metamorphic. The process of metamorphism is the process of heat and pressure applied to a rock, causing it to be changed, metamorphized. And finally, on the Mohs hardness scale, what is the hardest substance? Diamonds. That limits it to those 3. And what's the softest one? I noticed talc is spelled T-A-L-K in one place. Didn't notice that until now. What is the softest one? Talc. And so the correct answer there was E. All right, so we got another quiz in, hopefully raising scores. It's not the goal of the quizzes, but it's still a hope I always have. Because you know what I want? I want you guys to have great grades. That is the wrong class. You would be rather confused with quantum mechanics. All right, this is the correct class. First, just an advertisement. Tomorrow night at 7 p.m. in the auditorium here in the Kruger Center, room 200, Dr. Susie Phillips, she's an alumna of Union College, just to make sure we're all speaking the same English language. Alumna is the feminine form of a person who's graduated from the institution. A male is an alumnus, a female is alumna. Plural males are alumni. Plural females are alumni. And if you have mixed gender, you go with the male. So plural mixed gender is alumni. So she's an alumna of Union College. She is currently the chair of the Department of Earth and Biological Sciences at Loma Linda University, which for the last 5 years or so has been a division of the School of Medicine. They reshuffled things, and somehow biology and earth sciences, so geology is now something that's in the medical school. Makes no sense. But she will be here on campus for Alumni Weekend. She's coming in tonight, and tomorrow night she's going to give a talk on belief in a world of doubt. That is, we live in a world that scientifically does not believe in creation. And we've been looking at some things already in this class that are at odds with your beliefs as a Christian, or likely are at odds with your beliefs as a Christian. And so she's going to be giving a talk on dealing with those questions and doubt when you're looking at scientific interpretations of data and your Bible. So I would encourage you to attend if you can. Tomorrow night, 7 p.m., Crew Center 200, our amphitheater here, or auditorium in this building. So that's an ad. She might come into class Friday morning to talk for 5 minutes, but probably not, because you guys are not You are not the traditional demographic that's going to go study geology. Okay, we are going to pick up with the water cycle today. We're going to talk about water on Earth. But first, a question that was relevant to our lab and what we've just finished talking about. Where are you not likely to find a volcano? So 3 of these 4 are places where you would conceivably find volcanoes. 2 of them we've talked about specifically. The 3rd one, you've seen some example, but we haven't talked about specifically. And the last one is not a case where you would find them. Waiting on one. I understand it takes a while to get logged in.
You let me do it every time.
Yeah. Well, while she's still logging in, let's move forward. Keep working on it. I haven't closed it. Gabby, I'm going to ask 4 people, Gabby, Danny, Leslie, and Mariah, in case you want to know who's coming up. Okay, she's in now. I'm going to ask you, oh, come on. There we go. I don't know what you answered, so I'm going to go with what the answers were before you answered. B, okay. So I'm going to ask Gabby, to tell us what a convergent boundary is and why it is or is not the answer. And then we'll go on and do the same thing. So the next person will have the next one. So Gabby, what is a convergent boundary and why did no one say that that's a place where you're not likely to find volcanoes? In other words, why is it likely to have volcanoes?
Convergent, aren't those when things are coming together?
Right.
Moving towards each other.
And so why would you have volcanoes there?
Of the rocks, like the pressure pushing against each other melts the hot magma, I guess, or whatever.
It's not just the pressure putting them together, it's the sliding causing it to grind. Okay? Then Leslie, what's a transform boundary? And 6 people said you're not likely. They're actually correct. So why are they correct in saying that you were less likely to find a volcano there at the transform boundary than these other 3?
Well, I could be also, and if you want me to be completely honest, I put B because I know that the other ones we talked about them, and transform boundary that name did not sound familiar as somewhere where a volcano would be found. So that's pretty much all I know about that because I don't know what a transform boundary is.
Okay. Transform boundary is like the San Andreas Fault, where you have sliding like this, parallel to the boundary. So it's not pushing in, it's not pulling apart, it's sliding parallel. And so with the sliding parallel, you're not doing the grinding like when it's converging. You're not opening up a gap. You just have moving sideways. That's why it's not likely. So the correct answer was the transform boundary because it's not opening up a gap or grinding. Okay, next will be Danny. What's a divergent boundary? Why was it not the right answer? And so why would you be likely to have something there, a volcano there? Yeah, you're opening up a gap, magma's coming up. And so if it's enough magma coming up, you make a volcano. And finally, Mariah, a hot spot. What's a hot spot?
Isn't it like it's the man? It's like the magma kind of.
It has to do with magma. It's what we stayed in lab last week.
I know it's underneath
And then, like, it makes the volcano erupt.
Okay, the hot spot is where you have a magma chamber under the surface, and it melts its way through and makes a volcano. And so that magnet chamber, as the crust moves over, it will punch through different places, which we have like the Hawaiian Island chains, because it keeps punching through as the surface goes over that hot spot. Okay, so that there is our first clicker question. Now turning specifically to water. More than 97% of the Earth's water is in the oceans. Now that is current scientific understanding. You may or may not know that for the last 5 years or so, there has been adding scientific information suggesting that there's water down in the mantle. Specifically what they found is diamonds that are coming from deeper in the ground, I think at the boundary between the lithosphere and the mantle. I may be wrong on the location, but they're finding diamonds from down deep that have encapsulated in them structures that, as we understand it, could only form in an aqueous environment when you have some water present. And so that's telling scientists they now have found the first one, was just one diamond. And they said, there's enough water for a whole ocean down there. Well, that's a lot of extrapolation from one diamond. But now they found diamonds from many different locations that from down deep indicate that there's water. And so it may be there's a lot more water in this earth than we're aware of. But this is the standard knowledge that 97% of all of the Earth's water is in the oceans. So only 3% of the Earth's water is the water that we drink, bathe in, swim in, etc. And of course, not counting, we swim in the ocean. That's what my son's senior class trip is going to go do, to go into Florida so they can play in the ocean water. And so 97.2% of the Earth's water is salt water. That's water we can't drink because the salt would, dry us out. Another 2.14% is in ice caps and glaciers. If you add those together, 97.2 and 2.14 is going to be 99.3% of the Earth's water supply is either in frozen or ocean form. That means the water that we deal with is a really, really small percentage of the Earth's water, right? The water that's available for us to have streams, rivers, lakes, to drink, etc. In fact, 0.61%, if you take 0.61 and add to 99.3, you have 99.9. 0.61% is groundwater, and that's the water that is of interest to us. And then there's surface water. Surface water. What's surface water? Just trying to have you parse the words. That'd be like lakes and streams. That's 0.009% of the Earth's water is in lakes and streams. Yeah, that's not very much, right? I mean, you look at the Great Lakes. That's surface water. And tells you how much water we have elsewhere. And then soil moisture. Soil moisture, we'll see later in the slides, is soil that is wet but not saturated. Saturated means you can't put any more water in. Moist is it's wet, but you could put more water in. It would be able to hold more water. Okay, so let's talk about this hydrologic cycle. I have this picture in 2 slides. I'm going to talk about everything on this slide. The next slide I left in there simply because it has the 4 words bulleted. So when you go back and look at it, you'll have a slide you can look at with the 4 words bulleted. So here is the hydrologic cycle, the cycle of water. So the cycle of water is driven by heating from the sun. The sun heats things up. If it heats it up, you can change it from a frozen phase to a liquid phase, from a liquid phase to a gas phase. So that's the action of the sunlight. And then we have the force of gravity that pulls it down. So the actual hydrologic cycle is the 4 cycles you see in the picture. The 4 cycles are And I always start with evaporation. You have water that is either surface water. We have surface water here, surface water, or in the ocean over here, and it evaporates. So that's our first step, is evaporation. The water evaporates means it went from a liquid state to a vapor state, rises up into the air. Rises up into the air, it's what makes our clouds. Our clouds are water droplets that have condensed to go from the vapor phase into the liquid phase, but they're still being held aloft because they're tiny droplets. But those water droplets, if you get the right conditions, they can fall out, and that's precipitation. So precipitation is the rain coming down. And then you have the runoff running back into the surface water or the oceans, and it cycles around. So here are the actual words involved. I didn't talk about one of them. I didn't talk about infiltration. Infiltration is the water going through soil. So it's a travel through soil, whereas runoff is traveling above the soil.
So we don't need like condensation.
Condensation is actually part of what's going on in the precipitation. And so, yes, condensation is a good word to know. Condensing from the gas phase back into the liquid phase. That has has to happen for precipitation to occur. I'm sorry, I didn't mention it. Thank you.
Infiltration is under the soil?
Going through the soil, yeah. Whereas runoff is on top of the soil. Yes.
So hydraulic cycle is pretty much just where all the water goes. And
Hydrologic, but hydrologic cycle is the cycle of water going around, because the water comes to the earth, goes up to the sky, goes down to the earth, goes up to the sky. It's that cycle.
this is a more in-depth water cycle than what we learned in elementary school, pretty much.
I don't know. Depends on your elementary school. What did you learn in elementary school?
Yeah, just more in-depth.
Bigger words. Okay. Now some terms. Porosity. You guys know you have pores in your skin, right? They get clogged and you get acne and blackheads and stuff. Pores are holes. So porosity is measuring the holes in the soil. So a porous rock has lots of holes. A non-porous rock doesn't have lots of holes. If it has lots of holes, it has a high porosity, then a lot of water could be stored in the soil. A low porosity, it can't store much water. So what kind of water or soil has a low porosity? That's an easier one to identify. Can you think of a soil with low porosity that can't store much water? No? I tend to think of clays. Clays pack really tightly. And because they pack really tightly, you don't have lots of holes for water in there. So the porosity is actually measured as the ratio of open space to the total volume. And it is affected by the particle size. That is, if I have ping pong balls and I fill a box with ping pong balls, there's going to be lots of open space. If I fill the box instead with sand, there'll be much less open space because the sand things are smaller. And if I go to smaller things than sand, I'll have less open space. So that's where you get your clay. Your clay is particles that are much smaller than sand. And so they pack much more tightly, less open space, lower porosity. You might remember in your homework problem, how many people actually read the solutions to the homework problems?
Are you talking about in the back of the book?
No. After the homework's turned in, I changed the homework assignment to have a solution there. Well, in the solution I talked about, when you mix two fluids together, the total volume is always less than the volume you had of the two separate fluids. And the reason is because the molecules can conform a little bit and fit into gaps. Just like if you pour sand into a box filled with ping pong balls, you can pour a lot of sand in a box of ping pong balls and not have the level rise at all because you're just filling in gaps. Okay. Permeability. Permeability is the ease with which water can go through the soil. Now, oftentimes we think of porosity and permeability and get them confused. Porosity is how much water the soil can hold. Permeability is a measurement of the water going through the soil. Well, you could conceivably have a soil with lots of holes, but no pathway for water to go across it. Right? So you could have soil that has lots of little air bubbles, but each bubble has a complete wall around it. So it's very porous, but no water can enter those bubbles because they're sealed. So that would be a very low permeability case if all the bubbles were sealed, because water can't go through, can't get into them. So permeability is a measurement of how easily water can flow through. Porosity is about the ratio of open space to total volume. This word here, hydraulic conductivity, is telling us about how permeable the soil is, how easy it is for water to go through it again. So it's kind of a similar word. Now some more words. A lot of vocab here in the water chapter. We have groundwater. Groundwater is saturated earth. That's earth that is holding as much water as it can. So imagine that you have a tank and you fill it with sand. You start pouring water in, and water initially, you'll have wet soil throughout the sand. But the water will slowly, because of gravity, settle down, and you'll have a layer at the bottom that's completely saturated, filled with water, and then you'll have a boundary, and above that it'll be dry sand. And so the groundwater would be the water there in the saturated region, not the water in the, I said dry sand. If it's just moist, that would be soil moisture, but not saturated. So groundwater, if you drill a well and you go down below what we call the water table is the boundary between the groundwater and just moist soil. So if you drill your well below the water table, then the earth is completely saturated as long as it's permeable enough that water can flow into your well. Then you pump water out, and water will just flow in from that saturated soil, and you can keep pumping water out until the water table drops below the level of your well. Then you're in trouble. Here's a picture illustrating what I've been talking about. So you have water. Anywhere on Earth, there is a water table. If you drill low enough, you're going to hit water, saturated soil. The question is, how deep do you have to drill? As this picture illustrates, there are some things that you can take as a good rule of thumb. If there is a stream, the water table is going to be as high as the water of the stream. Otherwise, the water would just be going into the soil, and the stream would very quickly disappear. So your water table is going to come down to the level of the stream where the ground meets the stream. And because of gravity, the water table will probably be higher away from the stream because it's flowing down to get to the stream level here. So if you have a stream, you know, well, the water table is about that high, maybe a little higher here. So I'm at this house here, I need to drill down, and ideally I would probably try to drill down below the level of the stream just to make sure that if there's water in that stream, there's going to be water in my well. So you drill your well down, and you want to make sure you go below the water table, the line that separates the saturated from the unsaturated soil. And then you see that this is dipping down. Why is it dipping down? What's the well doing? It's pumping water out, and so water has to flow back into the well. Since it has to flow back in, it causes a short-range depression in the water table as the water is flowing in. So that's illustrative of how water tables work. Now let's imagine that you go and you buy property out in Colorado and you need to drill a well. How do you decide where to drill the well? What?
You have to be near a stream or something like that.
Okay, if you have a stream, that's a good indicator, right? If you're near a stream, you'll have a good idea. A lot of people do things, they'll hire somebody to come out and consult. And that consultant will be looking at geological charts of the area to indicate where the water table is. You know, here's a place where the water table is good for a well. Some people will hire a water witcher, a person who walks around with like a Y-shaped stick, or there's different variations of it. And they walk around and they say, oh, the stick goes down here. This is where you should drill your well. There's no science to that. Some people swear on it. But scientists tend to say, the truth is, for the most part, it doesn't matter where you drill. Drill where it's convenient, because that water table is not fluctuating heavily. So you're basically going to have to drill down to the same level just about anywhere you put it. And you just have to drill down until you hit water, because you're eventually going to hit water. But sometimes you chose a place where the water table is really low and you have to drill really deep. Sometimes you're lucky. My parents' home, there's a lake a mile away, and there's the canal system that runs right through their property. Well, water going through that canal, it does have concrete walls, but you know what? They're permeable. And so they help to keep the water table around my parents' house nice and high. So, 2 years ago, there were a lot of wells in Central California that were going dry because of California's drought. But my parents did not have that problem because of their location. Anyone besides Leslie, California? I know she's from the Central Valley as well, so this should at least resonate with her. Aquifers are reservoirs of groundwater. So anywhere where you have a reservoir of groundwater, it's called an aquifer. Here in Nebraska, we have a very, very important aquifer. You guys know the name of this aquifer that pretty much covers the entire state?
Oh,
the Ogallala Aquifer. So that Ogallala Aquifer is essentially this huge lake within the ground. It's not an empty cavern filled with water. It's dirt that's saturated with water. Yes?
How do we know what aquifer we have? Like,
okay, how do we know? Dude, it's a very good question, because you don't walk over the ground and say, yep, there's a big, big lake underneath me, right?
Whatever it's called. I was like, wait, what? I've never heard of it before.
Oh, you should have. With the whole Keystone Pipeline thing, I went and protested at the state capitol. I don't want them to put a pipeline that goes through the Ogallala Aquifer, because it seems every couple months there is a leak in these pipelines. And if oil spills into that Ogallala Aquifer, then you're now contaminating this huge underground aquifer, and the ecosystem is very damaged. That's a political view. I probably shouldn't go too deep on it, but it worries me. We had the same thing that was going on to a lesser extent up there in North Dakota. So how do they know that there's the aquifer there? How do we know anything? Number one is they're going to use things like seismic waves. They'll go and they'll thump the ground and look for local variations in the reflected waves to tell them about what's down there. So that's one way of determining. That's a very significant way of determining what's down below us. Another way is actually drilling. Drill down, see what you hit. So geologists have gone out and done a lot of studies to determine exactly what the extent is of this aquifer. No, I didn't even put these words in. These came from the textbook. It is important to keep this vital source of fresh water clean and contaminant-free. That, my friends, is why I went and protested at the state capitol building, which is conveniently only, 7 miles away. And you know what difference it made? This big. None. but I expressed my opinion. Artesian springs and wells. You've probably heard of an artesian well, but it may not be clear to you what it means. So here's what an artesian well is. It's kind of, you guys are too young to even have ever watched the Beverly Hillbillies, right? You have, okay. One day, Jed was shooting at some game, and up from the ground came a bubbling crude. Now that's oil, black gold, Texas tea. Those are lines from the song, by the way. But if it was water, that would have been an artesian well. Artesian wells are places where, you're just walking along and you're like, I'm going to dig a well here. And water comes bubbling up and you don't even have to pump it. It just comes up. Those are the good kind of well, right? It doesn't take a lot of work to dig that well. So why would water come bubbling up out of the ground? There's not a pump pushing it up. Why would it come up? Pressure. The driving forces for a hydrologic cycle were sun and gravity. Well, the sun is not going to do this job, but gravity will. If you have water in a water tank that's built up high, there will be pressure based on, remember, change in pressure is density times G times the height difference. So there'll be water pressure if you make pipes that come down from that water tank and go to your house. Well, the ground is the same thing. In the ground, you have an aquifer, and if one end of it is high, it's going to pressurize the water down below. And so this picture shows an aquifer starting at a high point. Water falls down to fill the aquifer. The water flows through this aquifer. Notice the little dots there representing it's going through soil. It's not a cavern it's going through soil. But the water level, the water table, is shown like this. That's the water table. So here, you have a hole through the rock where water could come up. Somebody dug a well, but water's not coming up. Why? Because the water table is below the surface. So you don't have pressure pushing it up. But down lower, you have a similar well, a hole through to the water table, but the water table is above the surface of the earth at that point. And so water comes right out of the ground. And that's an artesian well. Why is the water table dropping as we move to the right here? Why is it not staying at the original elevation? Why isn't the water table staying at this height all the way through? That's supposed to be a horizontal line, friends. That's closer to horizontal line. Why isn't the water table staying at that height? If it was a swimming pool, the swimming pool level would be the same everywhere. Agreed? And that's because of gravity acting the same everywhere. So here, why isn't it level like a swimming pool would be? Because of the what? Upward force? It's not an upward force. I appreciate you thinking that. As the water goes through the soil, it's not flowing freely. It's not like a swimming pool where there's no obstruction. There is soil that it has to go through. And so there's going to be some energy required for the water to push through the soil. And that's what causes the water table to drop, is because the water doesn't freely flow through. It has a restriction to flowing through. Thus, the water table drops as you go.
Wait, so does this all go back to what you were talking about with the permeability?
Yes. If the soil was very, very high permeability, that is like if it was just an empty cavern, then the water table wouldn't be dropping. But as the permeability gets lower and lower, the water table is going to drop more and more as you move away from your high point. So yes, it absolutely does. Another word for you, a perched water table. Perched water table, once you know that it exists, it makes perfect sense. it's a water table that is sitting above dry soil. Like, how do you get water table above dry soil? Well, you have to have underneath it a layer that is low permeability so water can't go through it. So that's what a swimming pool is. It's a perched water table. You have made a barrier that the water can't go through. Then you put water on top of it and it can't go through, so it stays perched there. Now, of course, a real perched water table is a naturally occurring thing. Notice this has a lens-like shape. It's got an upward curvature on it. Why does it have that? Because the water will slowly seep through the soil. It will slowly come out like this. And so, it might have started like this, and as it it might have started like this, but then it seeped away, and it's highest in the middle because it isn't seeping away in the middle, it's seeping away in the edges. So that's a perched water table. And of course, if you had your perched water table on soil that somehow had walls on it like a swimming pool, then it would do something like that. So perched water tables, they're not the best source for you to put your well into. Why is it not the best place to put your well? Yeah, it'll run out. It's a fairly limited water supply. Whereas if you get down to the groundwater, it's going to be replenished by a much broader system. Right? That perch system, maybe there's a stream that runs and fills it, but more likely it's just relying on rainfall. Well, as you start pumping water out, it gets less and less until you're like, oh shoot, now I have to drill down further to get down to the real water table. We're not going to do the math here with Darcy's law. Darcy's law is a law to calculate how quickly water flows. The flow rate has to do with the hydraulic conductivity. I've already described that. What is the hydraulic conductivity? By the way, there is a homework assignment due today, right? Just making sure we're on this page and I didn't, you're like, what? Yes, the hydraulic conductivity is a measurement of the permeability, how easily water can flow through. Cross-sectional area, if we're talking about a pipe, that's how big the hole is. The bigger the area, the bigger the cross-sectional area, the bigger the pipe. And then the hydraulic gradient, which is the thing that this picture is about. The hydraulic gradient is what is the vertical distance that the water table changes divided by the horizontal distance it changes over. That's the hydraulic gradient. And so if you have a bigger hydraulic gradient, a bigger change in elevation for the water table, then it's going to flow faster. Smaller hydraulic gradient, not much change in elevation, it's not going to flow very fast. The hydraulic head is the term for the height of the water table, usually compared to sea level. So hydraulic head water is this much above sea level. Although you could use it relative to the surface right here. Of course, that'd be a negative hydraulic head for almost everywhere, wouldn't it? Because usually the water is below the surface. Otherwise, you're in a lake. Now, interesting, fun stuff. I say interesting, fun stuff. That's not fun as far as money goes. It's really not fun if that happens in your Corvette museum. I don't know if you guys remember that happening. But there was a sinkhole that swallowed up, I think it was like a couple Corvettes or something. What makes those sinkholes? Yeah, you have the dirt underneath got dissolved or washed away. So if it's limestone, remember limestone is water soluble. And if you have groundwater that's flowing through limestone, it will dissolve it away. If you've been to, like in Tennessee, you have, I can't remember the name of the caves there. but you have some caverns that you can go into and look at all the great stalagmites and stalactites. There's a waterfall in there. All of that was created because you had water flowing through limestone. It dissolved the limestone and created this big underground cavern. And so sinkholes like this are examples where water flowed underneath and it washed away all of the soil. So all of the soil, okay, black on black is not working. All of the soil that was in here got washed away, and then the asphalt on top fell in. And if you're driving and that falls in, you're not happy. So sinkholes, caverns, and land subsidence can all occur because of water. Here is an extreme example of subsidence. This is where ground level was in 1977. This is where it was in 1955. So that's 22 years. The ground level dropped by that much. And in 1925, add another 30 years. So it's a total of 52 years going from the top down to here. That is a huge amount of subsidence. The ground level has fallen. This is in San Joaquin Valley in California, the Central Valley, the Fertile Valley. We grow lots and lots of produce there. I say we've got a little almond orchard, our family does. It's only 40 acres. It's not a big production. We use a lot of water in our agriculture, and that water's got to come from somewhere. And so what do? We do two things. We either pump it out of the ground or we rely on the California aqueduct system. You pump it out of the ground, there's less moisture in the earth so that the earth can compact more because it doesn't have moisture in there. And so this dropping is just because the earth is compressed when the water was pulled out. And it's a lot harder to put water back in than it is to take it out. So it's pretty much a permanent change, which means that the aquifer under the Fertile Valley will probably never be what it used to be because we've pumped it out. And so subsidence is the greatest human alteration of the Earth's surface. This is a big fight in California. I know we're not in California, but the agriculturalists are saying we need water. We need water because we can't grow food without water. And the environmentalists are saying you're using all of this water and it's not an unlimited resource. It is a big headache. I'm not going to come in on a side on this one. It's an important debate, and I don't know where the best answer is. But I do know that this is just about the best time for us to end class. So I've already talked about that. This is what causes ground sinkholes. We will stop here, and I'll see you in lab tomorrow. Assuming you